We now discuss piezoelectric resonance. As you know very well, any mechanical body can be excited, any solid body can be excited into mechanical resonance by applying forces to it. In a piezoelectric materials, one can excite mechanical resonance, mechanical vibration of the sample at a resonance frequency by applying electric field. And this is possible because piezoelectric materials can produce strains and stresses by application of electric fields. So how does this work? We cannot go into many details. I will basically just give you some basic information about piezoelectric resonances, and I hope make it possible for you to navigate through other more complete texts and examples that you will find in the literature. Again, the book by Ikeda is good, one by Berlincourt by Berlincourt, one by Ikeda. There is this paper by Old in the Journal of the Acoustical Society of America, and so on. There are indeed many of them. So we will consider piezoelectric resonator in D3-1 in transverse mode, just as we did for coupling coefficients. So we will assume that we have a sample which is long and whose length is much bigger than width, and width is bigger than thickness. So we can consider a problem in one dimension only. Typical dimensions would be something like 10, 5, 10, 2 and 0.1, 1 to 2, 0.1, maybe to 0.5 units, let's say millimeters. And we need to consider again the full set of constitutive equations. Which set to choose depends on boundary conditions, and for this particular set we can use these constitutive equations. Now, if you apply electric field on this sample, so these are electrodes, if you apply electric field at very low frequencies, the whole material will uniformly deform, and there will be no any unusual behavior. However, if we keep increasing the frequency at which we change electrical field, at some point when the wavelength of the acoustical wave, which is induced in the sample by the electric field through piezoelectric effect, when the wavelength becomes comparable to the sample dimensions, the stress sigma will no longer be homogeneous, and that is why we need to use the whole constitutive equations. Otherwise, we could just stop at these two terms, but with the increasing frequency we have to consider the whole set of equations. The stresses in sample will be inhomogeneous. We will have generation of the direct piezoelectric effect in addition to converse and so on. So the boundary conditions of the problem are the following. We have a constant field at the electrodes, so that's equipotential service. We have that epsilon 1 and epsilon 2 are zero everywhere. And we have that stresses are 0 along all directions in the sample, including shear stresses. Sigma 1 can change with the position, but at the end we assume that sample is at each end we assume that sample is equal to 0, that it is free. However, inside it can change with the position. So we will work with the frequency that are comparable with the natural mechanical resonance frequency of this piezoelectric body. We can derive, if we apply sinusoidal field, we can derive piezoelectric resonance. We can consider one volume in the sample and consider wave equation. So we start with the Newton's equation for this volume delta V, which displaces by some amount delta D. We calculate force, strain, and we put all that into wave equation and we solve it. And to find out we solve this differential wave equation, and to find these boundary, the C1 and C2 constants, we can use boundary conditions. And this equation here, V is velocity of the sound, where S is elastic compliance, and rho is the density. You can find this derivation, for example, in Berlin-Court book and in other books. I'm not going through this derivation, but you should be able to read what's written here from your mechanics courses. In any case, once we solve for these constants C1 and C2, which come from solution of the differential equation, the wave equation, we get that displacement of the sample as a function of x along the length of the sample is given with this expression here, and it looks like this. Here are the numerical constants that are used to calculate this displacement, and you see that they are on the order of tens of nanometers, which is much bigger than what you would get just for a static piezoelectric coefficient, where these displacements would be in picometers per volt, maybe hundreds of picometers, at least 10, 100 times smaller than what you have in resonance. And also, because these are trigonometric functions, we will find out that there are several solutions. For this particular one, there will be resonance at 200 kilohertz, then at 600 kilohertz, and then another one, I think this is wrong, it should be at 1000 kilohertz, so it should be 5 times, 135, I think so. You may check that. And the sample this plane wave that is propagating through the sample will change its form as the frequency is changed. The center is always a nodal point, and then you will have a different displacements at 0 and Lth and end position of the bar. We can plot this as a function of frequency also. We fix position, for example, end of the sample, and this is what I'm doing there. So I'm now fixing x and plotting as a function of frequency, and what you get is that delta is very small at low frequencies, and then at so-called resonance frequency it becomes basically infinity, which is not impossible in practice. There are always some losses, so it will be a finite motion, but much bigger than at static frequencies. And then displacement phase would change, so it would become negative as we go beyond the frequency, and then this will repeat itself as trigonometric functions are periodic in these changes. So the resonance frequencies are given by this expression here. Again, you have a length, you have density, you have elastic compliance, and n can be 135. That comes from a solution of the differential equation. Here I'm plotting as a function of radial frequency, and here it is the frequency in hertz. Now, it's interesting, since we have that displacement, mechanical displacement will go through a singular point through a resonance. It's interesting to see what will happen with electrical conditions of the sample. What we have here is that we are applying electrical field, because in homogeneity of the stresses and strains in the sample, we will also have converse direct piezoelectric effect, and we can expect some anomalies in the current. So let's calculate the current. This is the strain. This here is the charge density on the sample. We can put this strain there and calculate impedance, admittance, which is equal to current divided by voltage. By current we get by integral of charge density, and charge density is given here. We put it over here, and voltage is just integral of field over Z. And for impedance we get for admittance, for admittance we get this expression. Impedance is just 1 over admittance. Now this is purely imaginary. So the real part is equal to 0 here, and this susceptance is equal to frequency times capacitance of the sample. Now, if we assume that the permittivity is complex, then we would also have after calculation the real part of admittance, and that would be conductance. So we can plot both admittance and conductance. They will no longer be when we just have capacitance without conductance, when there are no losses, we have these singularities. But if we introduce conductance, then both real and imaginary parts will become finite, and we have these peaks in the current and permittivity or capacitance, which shows these resonances. Now, it is not true capacitance of the sample that goes through the resonances. The capacitance of the sample would go to resonances at much higher gigahertz and terahertz frequencies. It would go through relaxation or the resonances at much higher frequencies. What we have here is the consequence of piezoelectric effect, which at mechanical resonance due to inhomogeneous stresses through direct piezoelectric effect gives us a lot of charge, and it looks as though capacitance becomes negative and goes through singularities, but that's just effect of the piezoelectricity. So what you can do if you are working with resonance is take this really the simplest example. In this form, it is giving you only imaginary part, but if you replace all material coefficients, compliance, permittivity, and piezoelectric coefficient with the complex numbers. And you really can do it only for permittivity and elastic compliance. You can ignore complex piezoelectric coefficients. You put it there, and then you separate real and imaginary part. You will get such functions. You can see what is the resonance frequency, the frequency of the resonance. And you can change the values of dielectric and mechanical losses and see effect that will have on conductivity, on susceptance. For example, you will get that conductivity becomes broader and lower in a magnitude, and so on. So you can try to do that. Now, we can write this equation in a different way. We can take these terms here, take permittivity out, and you see when you do that you will get here something that is a coupling coefficient, the same coupling coefficient that we had before. So it appears also in the resonance equation. And now we can see why coupling coefficient is also an important parameter for resonances. You can completely eliminate D and S and look at everything just via coupling coefficients. Now, the resonances, the equation of the resonant behavior of impedance in the vicinity of resonance is very important, because we can use this to calculate different material parameters. For example, if we take behavior at the resonance frequency where permittivity goes, where admittance goes into infinity, we can find out, so we make this infinite, that's the only term that can become infinite here. We can derive what is the resonant frequency of the resonance frequency. And since we know length and density of the sample, and if we know elastic, if we know frequency, which we do know, we can calculate S11, we can calculate compliance or Young modulus, depending on in which form of the equations we are using and what resonating mode we have. Second, we can take these values where admittance is, if we plot a full admittance, which is equal to B square time G square, then you will see that it crosses zeros. And from if we put this equal to 0, these are the frequencies where admittance is becoming 0. We will be able from this equation to calculate coupling coefficient. Now, once we know coupling coefficient, we know S11. If we know capacitance, we can calculate permittivity. We calculate this from this equation here, then we can determine D31. And actually the determination of, for example, elastic constants from the resonance is one of the most accurate ways to calculate elastic constants and these other coefficients. You still have to be very careful how to do that. For example, which value of the permittivity you take, and so on. So here is how these real and imaginary parts of admittance and impedance look like. Here is definition of these different frequencies. I will not go into that too much. It's interesting to look at the impedance as a function of a frequency. It looks like this. So on a log scale, so this is close to resonance frequency. It's actually F minimum. Here is frequency of a maximum, which is close to anti-resonance frequency, but not exactly the same. Since you like operation at resonance frequency, either resonance or anti-resonance frequency, depends on your application. For example, if you work at resonance frequency, you would like to be as close as possible to the impedance of instrument that you are using this piezoelectric material with. And that internal impedance is usually 50 ohms. So you would like this to be as close to 50 ohms as possible. Also, note that at this frequency here, we are actually working, if you calculate elastic constant from this, you would be getting elastic constant under zero circuit conditions, when impedance under short circuit conditions, when impedance is ideally zero, while here where impedance is infinite, you would be working under open circuit conditions. So you can determine these different coupling elastic constants, and this is normal because these two frequencies are related to coupling coefficient, as you remember, and therefore it's normal that corresponding elastic constants would also be related to these different frequencies. Another thing which is interesting to observe here is if you look at the phase angle, you will find out that the phase angle is -90 below resonance and above resonance. So sample behaves like a capacitor. Then here where phase angle is 0, the sample behaves as a resistor, and here where the phase angle is +90 degrees, the sample behaves as an inductor. And this suggests to us that we can represent any piezoelectric material near its resonance under resonant conditions can be represented in the terms of an electrical circuit, which we call equivalent electric circuit. And here are 3 examples. This is the simplest one where there are no losses. So that was the first one where we had only imaginary parts. This is the one where we introduce mechanical losses represented by this resistor here. In an electrical circuit, the losses come from resistors. And this is the one where we also introduce the electric losses in addition to mechanical losses. You can reduce this equation if you develop it in a Taylor series around frequency of the resonance, and if you take n equal to 1, so for first harmonic, we can derive that the total impedance looks like this. So that would be this first term, and then we can add others, recognize what these other terms would be. So C0 describes geometrical capacitance. The C1 is so-called motional capacitance of the motional part of the circuit, where you have contribution to the capacitance from the directly from the piezoelectric coefficient. R1 is the mechanical attenuation, and L is given by this expression, here. So C0 would be capacitance which corresponds to epsilon U, which is clamped capacitance that would be above the resonance frequency. So the frequency dependency is given by these terms here. And these equivalent circuits are very important for devices. You can add to these circuits additional elements that will represent electrodes of the sample and so on. So you can numerically study different piezoelectric materials, effect of electrodes on them, and so on. So these are very, very useful. They are more complex circuits, for example, KLM circuit and others, but I will not be talking about that. So this completes our discussion of resonance. We will be mentioning resonances, piezoelectric resonances later on throughout the course, because many applications depend on them.